Okay, so we're going to go over the concept of the mole and Avogadro's number. Remember our definition of a mole is 6.022 times 10 to the 23rd of anything. So you guys are used to counting terms. This is another counting term. The counting term you're probably most familiar with, a couple of them, is like a pair. You know, if you have a pair of something, you automatically know it's two. Doesn't matter if you have a pair of shoes, pair of socks, so on and so forth. They're talking about two things. If you have a dozen, it doesn't matter if you have a dozen donuts or a dozen eggs or a dozen cats. You know that means you have 12. A dozen donuts is 12 donuts. A dozen eggs is 12 eggs. A dozen cats is 12 cats. That probably makes you a cat lady. Same thing with this number here. 6.022 times 10 to the 23rd of anything is called a mole. If you have a mole of marbles, you have 6.022 times 10 to the 23rd marbles. It would cover the earth 6 miles deep. If you have 6.022 times 10 to the 23rd dollars, every man, woman, and child on the face of the planet could spend $1 million an hour and still have most of the money left over after they spent that money their entire lifetime. So it's just a huge number. So in chemistry class here, times 10 to the 23rd is only going to go with super, 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 super tiny units. Things like atoms, ions, formula units, molecules, things that are so tiny that we cannot see them with our naked eye. So anything that is a particle or a piece. So 6.022 times 10 to the 23rd particles. That's what a mole is. Now we're going to do a lesson to try to understand how huge that number is. Because the problem is that when you're dealing with things that are super, super, super tiny or super, super, super huge, it becomes difficult to understand because it's a concept of exponential. So let's expand this. You guys know a little bit about scientific notation there when they write that times 10 raised to the 23rd? Okay, you probably learned about scientific notation in middle school. So I'm going to expand this number, meaning that I'm going to move the decimal point over 23 spots. So I want you to think of positive being huge. So that's a positive exponent that leads to numbers bigger than 1. Negative exponents lead to numbers less than 1. So I'm going to move the decimal point 23 places out. That means I have to add 20 zeros here. Like such. So we're going to spend a few minutes trying our best to understand how big this number really is. Let's deal with the concept of money. We're all familiar with money. So you got $1 in your pocket. That's all the money you have to your name. Kind of sucks. You can't even really get a lunch at the cafeteria. But you could probably get a snack. And let's start adding zeros on here and deal with numbers that we are familiar with. So I'm going to add 1 0 on there. You could get a pretty decent lunch for you and maybe even your friend who forgot their lunch money for $10. I added 1 0 on there. Not exactly changing our lives with that 1 0. That's a $9 zero. Let's add another zero and make it more interesting. Even though it's the same zero, right? It's the same number. Zero is worth $90. Let's do with $100. I'd probably go out to dinner or something. What would you guys do? Buy an outfit? Let's add another zero. And this zero is worth $900. Now with $1,000, what would you guys do? Video game, TV maybe? Let's add another zero. Because really $1,000, you can get yourself a nice toy, nice weekend away, but not that big of a deal, right? Another zero is a $9,000 zero. Now all of a sudden, 10 grand. Now things are getting interesting, right? What would you do with $10,000? Maybe a car? I'd probably buy a vacation. I love to travel. Let's add another zero. Look at one more zero, but all of a sudden, $90,000 zero. $100,000. Now things are starting to get really interesting. What would you do with $100,000? I might buy like a boat or a camper. You guys probably would buy your college education, huh? Would that even cover a college education? It'd be pretty close. I'm going to add one more zero. And again, even though this is still just a zero, this zero is worth $900,000. So even though it's just a round circle like the other ones, this zero is worth $900,000. And now you've got $1 million and you're a millionaire. Certainly doesn't mean what it used to, does it? What would you guys do with $1 million? I'd probably buy a vacation home, maybe. Or move out of this country, maybe move to France or something. Let's add another zero here. And we're going to have $10 million. With $10 million, you would never have to work again. You could live comfortably off the interest. This is a $9 million zero. And you would have no problems at all. You could probably even party with all rock stars and stuff like that. Maybe hang out with Justin Bieber. Whatever you want, because you're that rich. But let's add another zero, and you've got $100 million. You got $100 million, you'd have lots of friends, that's for sure. That zero is a $90 million zero. I add 1 0 to $100 million. What's a number called that's past $100 million? One more zero. You guys know? It's $1 billion. This is a $900 million zero. You got $1 billion, then you're officially in the top 1% of everybody in the world. Not the richest, though. You guys know, anybody know who the richest person in the world is? It just changed. Do you know? It is. He just passed up. Do you know who's number 2 now, though? Who did he pass up? So we've got Elon Musk, then Jeff Bezos. That's changed a little bit in my lifetime. Anybody know who number 3 is? Yes. It's still going to be Bill Gates, yeah. And Warren Buffett's up there. They kind of trade spots all the time. Bill Gates quit his job a long time ago and spends full time trying to give his money away. So now he has his own foundation and all that kind of stuff. And I guess that's a job in itself, but he spends full time trying to give his money away. Can you imagine having so much money that you had to spend all that effort just to try to give it away? But if you think about it, he stops to fill up his coffee cup, and how much money do you think he's made in that time? Lots. Sounded so exhausting to Warren Buffett. Warren Buffett's got lots and lots of money also. He said, "Oh, Bill, you're doing so good at giving the money away. You can give my money away too." Warren Buffett's story is actually really interesting if you've never watched it. Like, he's been paying taxes since he was 14 years old. He made so much money when he was 14 years old, he had to file a tax return. We're still not close. Let's add another zero. And you've got $10 billion. This is a $9 billion zero. Basically, you can't spend this much money in your lifetime, and your kids couldn't spend this much money in their lifetime. If you have $100 million, you're reaching close to what Elon Musk has. Elon Musk is, I think, like $185 billion he's worth. This zero is a $90 billion zero. So nothing's different about this zero except what it's worth. So even that, let's add 1 0, and we have 12 zeros behind it. What is 1 with 12 zeros behind it called? It is a trillion. So that's 3, 6, 9, 12. This is $1 trillion. Nobody on the planet has $1 trillion. So if you have $1 trillion, you're richer than anybody else on the face of the planet. But this is 12 zeros. This 12th zero here is a $900 billion zero. So this first zero here is a $9 zero. The last zero is a $900 billion zero. Can you try to wrap your brain around what this 23rd zero must be worth? That's what the word exponential means. It means that every single number after that becomes worth more. So that's that exponential curve that's going up. So you guys need to try to wrap your brain around a zero that is 23 zeros away. So now that we have, let's just pick carbon. Find carbon on the periodic table of the elements. So if you guys have your pink packet, you want to get that out. We're going to start looking at our pink packet. Does everybody here have a paper copy of the pink packet? And you guys at home, get your pink packet out, whether you printed it yourself or you got one in class. Again, if you want a pink packet and you don't come to school, you can have somebody grab one for you, a neighbor or a classmate, or you can just let me know and I'll leave one at the main south entrance for you. So everybody find carbon on this periodic table of the elements. Underneath carbon is its mass. What number is written underneath carbon? Yes. 12.01. What that means is that's the molar mass of carbon. That's the mass of 1 mole of carbon. So if I had 1 mole of carbon, it would be a tiny pile that would sit in my hand that would have a mass of 12.01 grams. So if I have 6.022 times 10 to the 23rd atoms of carbon, it would make a tiny pile in my hand. That's lots and lots and lots and lots and lots of atoms of carbon. And it would just make a tiny pile in my hand because each atom of carbon is so small that we can't even see it with the most powerful microscope. So you guys see carbon, you probably got carbon on you right now. Does anybody know what the common form of carbon is called? Elemental carbon. So if you're looking for elemental carbon, you can find it in two different common forms on the planet Earth. One of them is called graphite. Anybody know where you find graphite? It is your pencil leads. Anybody know why we call them pencil leads? What do you think? You would think it used to be made out of lead, right? And your parents are probably going to tell you that. But the thing is with lead, lead is a shiny silver metal, and it resembles all the other shiny silver metals. So I can show you lead, and lead is a metal. It always has the same properties. So pencils were never made out of lead. And you'll hear adults tell you stories about, oh yeah, I was stabbed in a pencil when I was younger and I got lead poisoning. Well, they probably got lead poisoning, but it's not from pencils. Pencils are always been made out of graphite. They think the reason we call them pencil leads is that back before, you might have seen in the movies, back before we had pencils, they would take quills, which are like the feathers for animals, and they would dip them in the ink. And that ink was likely lead-based. So you guys are in better shape than like my generation, because we were exposed to lead all over the place. Lead used to be a main component of paint. It used to be in gasoline. So when we would burn gasoline, there's actually a layer of lead all over all sorts of things because of that. And then they found out that lead causes brain damage. So they've been cleaning things up. But the properties of elements are consistent. There's also another common form of carbon. I'm guessing if you didn't know the first common form, we probably don't know the second common form. It's hard to believe we made it to January without talking about it, but I know we've had a little less time. The other common form of carbon is called diamonds. So that's elemental carbon also. Does anybody know why does some carbon form graphite and other carbon forms diamonds? What does it take to turn carbon into diamonds? Yes. Has to have lots of pressure, years and years and years and years and years of pressure, millions of years of pressure. So there's other forms of like things that what we would call gems. So diamond is called a precious gemstone, and then there's semi-precious gemstones. And some of the other precious gemstones are not worth as much as diamonds. Does anybody know anything about diamonds? Why would they be worth so much money? You might think that's because they're rare, right? But they're not even as rare as some of the other gemstones. The reason they're worth so much money is basically politics. One company got control of most of the diamonds, and then the areas that they are in are typically strife with political unrest and all that kind of stuff. So there's more going on with diamonds, but how we get a diamond is that carbon under the earth, elemental carbon, was pressurized over years and years and years and years and turned into a diamond. Technically, once you pull a diamond out of the ground, the laws of thermodynamics would state that they would start to revert back to graphite. But the problem is that's going to take millions and millions of years too. So we don't even know if that's going to happen. So in order to find the mass of 1 mole of any element, you would look on your periodic table of the elements. Okay. So now I'm going to show you what we're going to do with this information. So I'm going to introduce the concept of an equivalency statement. So an equivalency statement is 1 mole is equal to 6.022 times 10 to the 23rd particles or individual pieces. Doesn't matter what you have pieces of. Now, in chemistry class, we're never going to put the unit of grams or moles next to that big giant number. So you need to make a note for yourself. 6.022 times 10 to the 23rd only goes next to particles, which are atoms, ions, molecules, or formula units. For our purposes, you are never going to put the word gram or mole next to this. It's too big. The reason is, if I had 6.022 times 10 to the 23rd grams of anything, we wouldn't even be able to fit it in this room. It's just too big of a number. So that big giant number only goes next to tiny, tiny, tiny units. This is called an equivalency statement because of the equal sign. I'm going to turn this into what's called conversion factors. Conversion factors are how we convert from one unit to another, and you guys are going to start converting as early as tomorrow. So the conversion factors that I can get from this are either 1 mole over 6.022 times 10 to the 23rd particles, when you have a conversion factor, the quantity on the top is exactly the same as the quantity on the bottom. My other conversion factor is 6.022 times 10 to the 23rd particles on the top in 1 mole. Which conversion factor you use depends on which units you need to cancel out. So here is so in your pink packet, you guys find the page that looks like this. This is called a mole card. So this is in your pink packet, guys. Everybody find this. When I say go to your mole card, this is where you want to be. And we're going to be on the white side so far. We will not go to the dark side until next week. So we're going to be over here in this side, and we're going to be using these 4 boxes: mass, moles, particles, and volume. If you're looking for the mass, you're going to look on the periodic table of the elements. So I'm going to pick an element out of random. Does anybody have a favorite element? Oxygen should probably be our favorite element, right? How about gold and silver? Those are good ones. They're worth lots of money, aren't they? Another one worth lots of money that I love is titanium. But let's go with platinum. Find platinum, PT. He's at number 78. So my equivalency statement for platinum that I'm going to get off the periodic table of the elements is that there is 195.1 grams of platinum in 1 mole of platinum. So I can get 2 conversion factors off of this equivalency statement. Remember, equivalency statements sign, my conversion factors are made from my equivalency statements. So 195.1 grams of platinum in 1 mole of platinum. The other conversion factor would be 1 mole of platinum has 195.1 grams. So my units are grams in here and moles. Those are the two units in this conversion factor. And my labels, we're going to call them, are the platinum. I'm going to add one more equivalency statement and conversion factor that you're going to be using for these conversions, and that's in 1 mole of any gas at STP, what STP means is standard temperature and pressure. STP is about where we are at room temperature. So standard temperature is, it's kind of close to STP, but it's close enough where it works for us. Can anybody, what do you guys know about temperature? What do you think the temperature is in this room? 70 degrees, and that's in Fahrenheit. In science class, we're going to be using Celsius and Kelvin. Does anybody know anything about Celsius? What do you think the Celsius temperature is in this room? 30-ish? We're going to, you know what, and that's an excellent reminder for me, is I do want to go over Celsius to Fahrenheit, because if you guys are in a different country, I don't know if you know anything about other countries compared to us. We're pretty stubborn in this country in that we insist on using this old English system. The old English system is antiquated, and that's what Fahrenheit is. So if you go to Australia and you ask them what temperature it is outside, they're probably going to tell you 30 degrees. You don't want to grab a parka if they tell you it's 30 degrees, because they mean 30 degrees Celsius. So here's our first way we're going to peg ourselves so we can kind of get comfortable with Celsius to Fahrenheit. So 82 degrees Fahrenheit is 28 degrees Celsius. So they're mirror images of each other. Room temperature is usually about 21 to 23. I don't really even know what temperature is in here in Fahrenheit, but it's probably somewhere between 21 and 23 degrees Celsius. So that's a pretty good guess. And we'll get more comfortable with Celsius to Fahrenheit. So 1 mole of any gas, it doesn't matter the identity of the gas. It could be oxygen gas. It could be carbon dioxide gas. It could be chlorine gas. It could be helium gas. It could be neon gas. Has a volume of 22.4 liters. And we'll put at STP at the end, which we won't keep using that STP, but just to keep you remembering that 1 mole of gas has a volume of 22.4. When you look on your mole card here, guys, you'll see that those numbers are written there for you. So you don't need to memorize these, but you do need to know where to find them. This will be available to you, your mole card and your pink packet, for any quizzes and tests that you might take. So don't think that Miss Boston here wants you memorizing a bunch of numbers, because that's not the way I roll. Just make sure you know where to find them, though. So now I'm going to turn this in from equivalency statements into conversion factors. 1 mole has 22.4 liters, as long as it has to be a gas, though. And then 22.4 liters are in 1 mole. So you guys can take any equivalency statement and turn it into a conversion factor. We'll practice doing that, and then I'm going to show you how to use these equivalency statements. Okay, so let's pull up Google Classroom here. If you go into classwork, you're going to remember that we started the mole at the beginning of I mean, at the end of last semester. Okay, so here's the mole concept. This is the worksheet you're going to be dealing with first. I am going to extend the due dates because we do have some students who weren't even in the class with us last semester. So we're going to extend the due dates. If you are new to this class, you probably want to watch that mole video that walks through it in a little greater detail of what a mole is. So let's say, for example, well, we'll read the directions first. Correctly complete the statements below. You may need the periodic table in your reference packet. Remember to use 4 sig figs. Sig fig is short for significant figures. This relates to the number of grams only, because on your periodic table of the elements, you will notice that all of the digits are written in 4 numbers. There's 4 significant figures. That's why your mass will have 4 significant figures. So if you go to number 3, it says 16.00 grams of oxygen. That's what we mean by 4 digits and 4 significant figures. And it only relates to the number of grams. So in chemistry class, the number 16 and 16.0 and 16.00 and 16.000 are all different numbers. See, in math class, they might be the same number, but in chemistry class and science class, they are not. So anytime you have a number that comes off your periodic table of the elements that belongs next to the unit of grams, you're going to use 4 digits. So incidentally, number 3 says 16.00 grams of oxygen is in 1 mole of oxygen atoms. That's the correct answer. So now you have the tools to do all of this particular assignment. So give me a second